carbon dioxide and hydrogen ions. We're going to add to that now by looking at taste and smell. Taste is gustation, smell is olfaction. Both of these involve the use of chemoreceptors. It's interesting to note that taste and smell are, to some degree, intertwined, interrelated. We know that if our nose is all clogged up, we don't taste as well. It's not only that we don't smell as effectively, our taste is affected. If there is a person is smoking, it can affect both their taste and their smell. So there's a number of things that can be an interrelationship between the two senses. Looking at taste first, we have a number of different taste buds in the mouth and throat, especially on the tongue. These taste buds, if you picture an orange, a peeled orange, and you know that there's the segments of the orange, the taste buds look quite similar to these orange slices around. And within these orange slices, you have some taste cells, gustatory cells. These cells are going to have the chemoreceptors in their membrane that will respond to chemicals in the food, for instance, that we eat. In addition, these taste buds will have basal cells, shown here. The basal cells do have mitotic activity. They can divide and differentiate to replace the taste receptor cells. The taste receptor cells themselves do not divide, but you can regenerate them through the division of the basal cells. In order for something to be tasted, it has to first dissolve in the saliva. If you do a little experiment, if you take a napkin or a paper towel or something, and you dry your tongue off really well, then you put a little bit of sugar on the tip of your tongue. You won't actually taste it until enough saliva comes back for that sugar to dissolve in your saliva, and then you will be able to taste it. So it has to be soluble and dissolve. This shows you some of the places that we might have taste buds. This is a histology slide down here. This is a taste bud right there. Another one here. And they have little pores, taste pores there. If you use your imagination a little bit, maybe you can think of these like orange slices, and that's kind of their shape. And then within there you have the gustatory cells and the basal cells and supporting cells. And again, the basal cells, which are towards the base, as you might expect, can differentiate and divide and differentiate into gustatory cells. There are two different cranial nerves that convey the information, action potentials about taste, ultimately to the cerebrum. And those are, as we'll see later in the notes, but those are cranial nerves 7 and 9, the facial and the glossopharyngeal. Those two, part of their function is to convey taste sensations. We have several submodalities of taste. Here's the main ones listed here: sweet, sour, salty, bitter, umami. Umami is like monosodium glutamate.
I had a quick question, which was, you said that in order for something to be, in order for you to taste something, it has to be soluble. So I know that certain oils can have taste. Is that because of impurities?
I think you can dissolve to a degree, it's just that they're not extremely soluble, but you can solubilize them enough in the saliva to get enough of it to be a taste, because you don't need much to be. So it's true that oils are not very soluble in watery saliva, but enough to get to the taste. Yeah. So you are tasting the oil, not just an impurity. When you look at MSG or monosodium glutamate, you're really having a glutamate bind here. Some of these others, sweet, of course, if you look at sweet, sour, salty, bitter, you're going to open different ion gates. Salt is opening sodium ion. Sour is blocking. You have hydrogen ions and you block potassium efflux leaving the cell. Sweet is a G protein or cabotropic, binding glucose or sucrose or other substances. Bitter, a number of things can cause that. That's a G protein. Umami is a G protein. So these are G proteins. The first ones are just direct ionotropic, salt and sour, but the others are G protein by and large.
What are you doing specifically for the
You should know, yes, it's specific. It's pretty fast alone. Salt is sodium makes sense. Sour, hydrogen ions blocking potassium efflux. The others are just a variety which would work through a G protein. No, to that level, I don't think we expect any more than that. Like most senses, the sense of taste is first carried to the thalamus and then directed to the gustatory center in the cerebrum, which is shown right here. This information is conducted by, again, cranial nerve 7 and 9. And this is where it is. You should know where all of these senses are perceived. Here's our somatosensory cortex for our general. Here's the vestibular cortex, which we'll be talking about later. Here's olfactory, which we're going to be talking about just coming up very soon. Here's the auditory, here's the visual, for instance. This is gustatory here. Olfactory, we have an olfactory epithelium in the upper part of the nasal cavity. Interestingly enough, our olfactory receptor neuronal cells only survive about 2 months. They don't divide, but again, they can be replaced by so-called stem cells in that olfactory epithelium. There are cilia on these cells, and they have these molecular receptor proteins in the membrane, and they can bind. And of course, the sense of smell or olfaction is carried to the cerebrum by the olfactory nerve, cranial nerve 1. Notice that olfaction is the only sense that doesn't go through the thalamus before it gets directed to the cerebrum. It goes directly to the cerebrum. So that's something that's that's unique about it. This is our nasal passage. Up at the top here of the nasal passage, we have this olfactory mucosa. And that olfactory mucosa, it contains the olfactory cells, receptor cells. And here's our stem cells that can divide and differentiate into olfactory cells. There is a cribriform plate here in the bottom of the skull, and there's little holes in it. Olfactory foramina. A foramen is a hole, foramina is little holes, and these nerves from the olfactory nerve come from the mucosa up through and then form this olfactory bulb and the olfactory tract, olfactory nerve essentially, and that goes straight to this area here. that's carrying it through there. For something to bind to these chemoreceptors on this olfactory cells in the olfactory mucosa, it has to be both soluble and it has to be able to travel in the air as well. What's the word chemical word for that? Forgot. Aerosol. Anyway, it starts with an A. I'm gonna say aromatic, but I don't think that's it. There's somewhere it has something that's traveling in the air, but aerosol. Close enough. I think that's it. It has to dissolve both in the air and in the mucosa in order to travel. So that's something that's unique about olfaction. Olfaction is always transduced through a G protein. So G proteins, cyclic AMP production. We can smell 10,000 different odors, but we have only about 400 receptor types, but there's a mix and a matching that can occur. And this is where it moves to, but it doesn't go through the thalamus. Note, there's a number of things that can affect our sense of smell that are listed here, attentiveness, hunger. You probably are aware that on average, women have a better sense of smell than men. Smoking, of course, is going to decrease it. Age is going to decrease it as we get older. Things of that nature. Congestion can decrease it temporarily. Some people are born without the ability to smell because they don't have the genetic mechanisms to make the protein receptors. But that's pretty rare. Sometimes a decrease in our sense of smell can indicate possible diseases. We're probably aware that sometimes people who have COVID have some loss of sense of smell. People who are developing Parkinsonism can sometimes have a reduced sense of smell.
Yeah, I was just about to ask about like with COVID, why are there some cases where like people who like had COVID still don't have, or like they feel like they still don't have their full either taste or smell back?
I think the virus damages some of those cells that are responsible for that, and so they'll probably eventually regenerate and get it back, but the virus probably damages it. And that's one of the things, isn't it? They say, well, if you lost your sense of smell, you're gonna maybe have COVID, but there's a lot of people who get COVID that don't lose their sense of smell, or it doesn't seem to decrease. So it doesn't seem to be universal. Different people react differently, but that's what I would hypothesize, I guess, is that it's damaging those cells a bit. Anything else we want to chat about with taste or smell? While you're thinking, I'll mention another thing. The olfactory perception area there is really in the limbic system. And that has implications because smell and emotion are also somewhat interrelated, aren't they? We could give examples that you probably feel pretty comfy with. If you've been dating somebody and they wear a certain type of perfume or cologne, and then you break up, and a year later you smell that same perfume or cologne on another person on the elevator, it might bring a bunch of emotions back, just that smell, that odor. You may also have a situation where a child had a bad experience later, they smell that same odor and they get all panicky or distressed, and they're not sure why. They don't really remember why, but the smell triggers some bad emotional feelings. Sometimes we use certain smells to make things more attractive or sell things. If you're gonna sell your house and the visitors, prospective buyers are coming, your realtor may say, oh, bake some cookies or some bread and put that out. They come in, smells wonderful, cookies, smells like home. Hey, let's buy this house. There's that kind of triggering a little bit with emotion and smells that can do it. And that's really, it's part of the limbic system as well. So there's a linkage between smell and taste, but there's also a linkage between smell and emotion. Either good or for bad, it can be. All right, well, what about the vestibular mechanism? When we're talking about vestibular mechanism, we're talking about equilibrium and balance. The part of the inner ear that is responsible for this is called the vestibular apparatus. And so that's, we're associating that with equilibrium and balance. But the vestibular apparatus in the inner ear is only one piece of the puzzle for equilibrium and balance. By the way, the inner ear transduces not only equilibrium and balance, but also hearing, just another part of the inner ear. We're going to be looking at both of those aspects. The cochlea, the snail shape that we'll see, is for hearing. The rest of it is for equilibrium, the vestibular area. When we're looking at this, the output, part of what we need to control our eye movement. Do you know that our eyes are constantly twitching around, moving? We're trying to keep the center axis in focus, and so they're constantly making these very quick movements. And as we're moving, they have to adjust to that as well. That's part of our equilibrium or balance. And of course, we need to maintain our posture and balance and our awareness of our body position. So all of this is going to be important. Well, we've alluded to the fact that balance, equilibrium, is not just due to our vestibular apparatus in our inner ear. It's also due to vision, touch, and proprioception. We can do an experiment. You would be much better at this because you're a lot younger. But if you can stand on one foot pretty well, but now try it with your eyes closed. I'm already pretty shaky. You take vision out of the mix, it affects our balance. Now we can add some help back into the mix by touching. Now we have another point of reference, even if it's pretty light touch. And so, touch, proprioception, and vision work together with our vestibular apparatus to keep our balance. Proprioception is essentially knowing where our arms and legs are in space. We can do that easily without our eyes being open, our vision. We can do this kind of thing. And we know where they are. Well, proprioceptor receptors are like muscle spindles in our muscles and Golgi tendon organs, things like that. Now you might say Golgi tendon, or what in the world is that? Well, Golgi tendon organs are primarily in our ligaments and tendons, and they prevent overstretch, but they also give us some proprioception information. If you ever had a sibling if you have a sibling, they probably did this to you sometime. You were walking along, minding your own business, they came along and they hit you right there, and you had a little knee collapse. That's your Golgi tendon organ. It's, if you stretch it too much, punching it there, it's saying, oh, my tendon or ligament's getting stretched too much, I'm gonna collapse it so it doesn't rip, okay? And so that's part of it, all those kind of things that are helpful. So, here's our vision coming in. Here's our vestibular apparatus. That's from the inner ear. And joint, tendon, muscle, cutaneous receptors. That's proprioception and touch. Cutaneous, remember, means skin. So all that's coming in. And then we're getting some information going back and forth to the cerebellum from the vestibular nuclei and the brainstem. And then we have an output. This is input here, from up here. And then the output's going to our oculomotor center, controlling our eye movement, keeping the focus there, and then controlling our body movements, our muscles, if you will. So these are the outputs here. So we're looking at that. Now, if we look at the inner ear mechanism, we have a outer ear, a middle ear, and an inner ear. We're going to look at that in some detail for hearing. But this is the apparatus in the inner ear. And we have a cochlea, snail-like structure, and that's going to be where we transduce hearing. And then we have this vestibule and the semicircular canals. All that's part of our vestibular apparatus. Now for both, we have an outer bony labyrint, bony area, and then we have a membranous labyrint, which is shown in dark blue. The light blue out here is the bony. And then we have fluid between the bone and the membrane, like right here, all the way around. We have perilymph fluid. Peri means around, surround. And inside of the membrane, the membranous labyrint, in the dark blue area, we have endolymph. And that's in the cochlea and in these semicircular canals. The vestibule is sort of, the word means an outer room or an entryway. If you go into the church and you're going to the first part, well, that's the vestibule. Then you go into the main sanctuary, right? So you have the vestibule. We have two equilibrium sense organs there, and they're called the utricle and the saccule. That's their name. The utricle and saccule are going to detect linear movement. They are in the X and the Y axis, X and Y axis. The utricle detects the X motion, horizontal. And the saccule detects in the Y orientation, vertical. If you ever go to California Adventures and you take that California Screamer and you go from 0 to 60 and like nothing flat, and you're pushed back, that's your utricle detecting that acceleration on a horizontal plane. If you do the Tower of Terror, which I don't think they have anymore, and you go down real quick, that's the saccule, the vertical. An elevator would be a much less dramatic form of the same thing. So we have those two, the horizontal, or X, and the vertical, the Y. In addition, we have a number of different senses in these three semicircular canals that detect changes in fluid. And because these three semicircular canals are in three different orientations, it can detect rotational movement. Now, these utricle, saccule, and semicircular canals all work together. They're not working independently of each other, but they're evaluating different aspects. Both hearing and equilibrium, by the way, that information is carried by action potentials along the vestibulocular nerve, cranial nerve 8. Here it is, vestibular and the auditory or cochlear nerve, and they join together. Part of this detection is impacted by little hair cells. They're called hair cells because they're so small. And on these hair cells, these sensory receptor cells, on the surface, you have these little structures shown in the diagram. You have stereocilia, which are not true cilia, by the way, but they're sensory detectors. They're really more like flagellum. You have these stereocilia, and there's a group of these, several. And then you have one larger kinocilium, and they're all interconnected, like tufted together, like shown here. This is an actual electron micrograph. This is a kinocilium, and these are stereocilia here. So they can move as a unit. And when they move, there's mechanical receptors that can open ion gates or close them. At rest, when they're all vertical, like this, the stereocilia and the kinocilium, you will have a certain proportion of gates open, and you will get a certain amount of action potentials. These are action potentials represented here, same amplitude and a certain frequency. If you bend the stereocilia towards the kinocilium, as shown here, you will open more gates and you will increase the depolarization, and you will get a higher frequency of action potentials, as shown here. If you bend the stereocilia away from the kinocilium, you will close gates and you will have fewer action potentials. Now, if you're getting this information from several different sources in the inner ear, the brain can quickly put all that information together and plot exactly your position and how fast you're moving, accelerating or decelerating, and in what plane you're moving. And this is how we do our equilibrium. Now, I'll mention this again, both for equilibrium and hearing, we have an exception here. We've really tried to emphasize that pretty much everywhere in the body, we have a high concentration of sodium ions outside of the cell and a high concentration of potassium ions inside the cell. In this little microenvironment of the inner ear, we have a high concentration of potassium ions outside of the cell. It's an exception to our general rule. We actually pump potassium ions out of the cell in this little microenvironment. And so when we're going to cause depolarization, which leads to more action potentials in cranial nerve 8, or fewer, we're going to close them. It's potassium gates, not sodium, that we're opening or closing. And if we open potassium gates in this environment, potassium rushes in down its concentration gradient and causes depolarization. And if we close more potassium gates, we get a relative hyperpolarization comparing to our at-rest status. You feel okay about that? We're also going to be using the neurotransmitter. The neurotransmitter is glutamate for equilibrium and hearing. So we'll just mention that while we're here. Now for the utricle and saccule, we have a little different mechanism than we do for the semicircular canals. The utricle and saccule, just to remind us, are in the vestibule in this area here, not in the semicircular canal. And what they have is they have these hair cells. Here they are in the diagram, here, 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 and here. And they have the kinocilium and stereocilia. But instead of in fluid, these stereocilia and kinocilium are sticking up into this jello-like substance that we term the otolithic membrane. And on the surface of the otolithic membrane, you have some calcium carbonate, little pebbles or little structures, and they can roll around as we move our head around in a horizontal or vertical plane. And that pulls on the gelatin, the otolithic membrane, and that can pull the stereocilia either towards the kinocilium or away from the kinocilium. If you put it towards the kinocilium, you're going to open more potassium gates, get a depolarization. If you pull it the opposite way, you're going to get a hyperpolarization and fewer action potentials. Again, that's in the X and the Y. Utricle is horizontal, X, saccule is more sensitive to the vertical, Y. Now, in our semicircular canals, in other words, in here, in the indolent, we have a number of structures. The entire sensory structure is called the cristae ampullaris. You can see it encompassed here in our diagram. This is inside that membranous structure with indolent. And so there's fluid, indolent fluid around here. This membranous structure here, as part of the cristae ampullaris, is called the cupula. And that can bend one way or another. It bends due to fluid movement in the semicircular canals. If you turn your head one way, the fluid goes the opposite way, and that bends the cupula. You turn it the other way, the fluid goes the opposite direction and bends the cupula the opposite way. But we have many of these throughout those three semicircular canals. So you're getting info from all over the place. So as you're turning and rotating and doing back somersaults and doing all that, you're getting all this information going to the brain from these cristae ampullaris sensory structures in your semicircular canals. So you're making a constant plot. X, Y, and Z is added in. So you're constantly, oh, I'm here, and I'm here, I'm here. If you're doing snowboarding and you're doing a big dive and a backflip, you're also using your vision, where's the ground and all that, but you're using that. But you can sense, oh, I'm under-rotating. I gotta pull out of this thing in the middle so I don't do a face plant. You gotta pull out of it so you land, hopefully, and not crash and burn. So you're constantly reevaluating this as you're doing it. And so it's rotational for all sorts of normal activities, but certainly any kind of rotational activity is going to be a part of that. So all of these are working together, but these are giving us rotational. And this is our 3 planes of section, 3 semicircular canals as we're rotating. Here's the ampulla, this is indolent, here's the cupula, here's our hair cells. They still have a kinocilium and cilium, but now they're sticking up into this cupula, which is being displaced by our indolent fluid as we rotate. Rotating the head, rotating the body, which rotates the head. All of this is doing that. Again, here's our resting activity. The stereocilia and kinocilium are vertical, and we get some potassium gates open, and so we have some action potentials. Here it is when they're moved in the direction towards the kinocilium, and you get more potassium gates open, more action potentials. Here it's moving away in the opposite direction, and we get hyperpolarization and inhibition. Of course, some will be moving towards, some will be moving away from, depending on their location, and so the brain will interpret all of that to tell you where you are at that particular moment in time. These action potentials are along cranial nerve 8. That's where they're coming. Now, they're going to go to the vestibular center. Let's just go back quite a ways here. They're going here. But you send a lot of signals over to your cerebellum as well. The cerebellum sends signals back and forth. One of the advantages of the cerebellum is if you're in the middle of a movement, the cerebellum will you'll get sensory information coming up to your cerebellum, which will analyze it and say, you're a little off track, and it'll send motor back down so you get back on track. So it's changing your movement as you're making the movement. And the cerebellum has motor memory of our motor tasks that we're doing. So it can help with that. This is why the cerebellum is also important in equilibrium and balance, because we're moving our muscles to keep us in balance. So we're getting sensory information, and then we're moving to stay in a balance. If we trip unexpectedly on a crack in the sidewalk, what do? We move things out quickly to compensate so we don't fall, hopefully. And the cerebellum is involved in that. Well, it's the vestibular mechanism in our inner ear that's telling us a lot of that. Whoops, you're tripping, you're moving, along with proprioceptors and vision and everything. But that's all integrated very, very quickly, and we have to output it to our muscles so that we don't fall. And that's the mechanism. We know that if the cerebellum gets inhibited by drinking too much alcohol, we lose coordination. And if somebody was driving under the influence, they might have them walk a straight line, close their eyes and touch their nose. They want to test, is the cerebellum inhibited? Because maybe had too much drink. That's kind of what the test is looking at. So all that's part of this. Now, because this is showing us this, here's the cerebellum's role and all the others. Well, a little bit more before we go on to hearing, and that is what causes motion sickness. Well, motion sickness is receiving conflicting information to the brain. If your vision is saying one thing, and your vestibular apparatus and your proprioceptors are saying another thing, that conflict in some people causes this imbalance, loss of equilibrium, and even feel sick, like you can throw up, you might even throw up. Vertigo. If you're reading in the back seat of a car, or the front seat, but you're reading, your eyes are fixed, but your vestibular apparatus is saying, we're moving. Now, some people it doesn't bother, but a lot of people it causes that conflict, vertigo and dizziness and all of that. That's why if you're on a boat, it's moving up and down, your eyes are trying to adjust, whoa, we're moving here, and the eyes are here, and it's a disconnect. Now, some people genetically, it doesn't bother them to have that disconnect, but many people do when you have that disconnect. Most people that suffer motion sickness suffer more greatly when they're younger, when they're children, and then it lessens as they get old. It doesn't go away completely, but it lessens oftentimes as they get older. And genetically, again, there is a relationship, but like I get motion sickness, but my brother doesn't get it at all. It doesn't bother him. English Channel one time, and he was like totally fine, and it was a rough crossing. English Channel is kind of notorious as a rough crossing, and I was feeling like not so good, and he was looking, and he said, "Oh, look, they have pea soup for lunch," and I'm like, ah. So it's genetic, but it's not all, it's siblings that can have differences in it as far as that goes. Anything else we want to chat about with equilibrium or any of that? Okie dokie. Well, let's just do a hearing a little bit. We'll just get started with it. And, of course, continue on tomorrow. We're going to be doing the rest of the chapter hearing and the division. And we'll be the rest of the way. Then we're going to do the muscle. And then we have our next test a week from Thursday. So we're kind of pushing along here towards that. Well, hearing is also transduced in your inner ear, only it's the cochlea. It's conducted by cranial nerve 8 to the thalamus, but it gets perceived in a temporal lobe in the auditory area. So a little bit difference there. We have two main submodalities for hearing. First of all, hearing is air pressure waves. There's no sound in space because there's no air for the molecules to bang against. But here we have an atmosphere and we have air. So it's a type of mechanical transduction. We're going to use hair cells as well. The submodalities are frequency and intensity. Frequency is how many pressure waves you have per second. We often measure it in cycles per second or hertz that you're familiar with. And intensity is the higher the amplitude change in the wave, the greater the amplitude. Now, the greater the frequency, the higher the pitch. The lower the frequency of the waves, the lower the pitch. For intensity, the greater the amplitude, the louder, which is measured in decibels, and the lower the amplitude, the softer. We can change the pitch. This is a tuning fork, and you whack it and you get these waves. If you chucked a rock in the middle of a lake, you'd see these concentric waves, but you also get that in the air. And they have the amplitude, and they have the frequency of the waves. So we're looking at those two things. If you're playing a stringed instrument, a guitar or violin or what have you, and you hit the string and it vibrates at a certain frequency, right? And that frequency gives it its pitch. If you press on the string and you make it a different length, it will vibrate at a different frequency and you'll get a different pitch. Okay, the pipe organ in the church has all these different pipes, and if you blow air through them, the size, the diameter, and the length of the pipe will give you a different pitch, a different frequency of waves. Well, the loudness is you hit the string harder, or you push more air through the pipe or whatever, and you change the loudness, the amplitude, the intensity. So these are the two submodalities of hearing. Loudness is measured in decibels, and it's a logarithmic scale. Okay? So you can see a logarithmic scale, it's going to be a one-fold increase in decibels is a 10-fold increase in intensity. This is not to memorize this decibels, it just gives us an idea. First of all, 0 decibels is the average that a young person can just start to hear a sound. Some of you would have, most of you, would be able to hear in the negative decibel range because you have better than average hearing. And so you might hear -1, -2, or something like that. But 0 is the average where the population can just hear a sound. And then it goes up from there. You can hear the whisper, normal conversation, heavy traffic, all the way up. It has energy, so we can damage our hearing mechanism if the sound is too loud. It can actually cause damage, and of course, you don't want to get behind a jet plane with an afterburner. You're going to blow out your ears. If you work in the military and you're in artillery and you don't put any hearing protection, you're going to damage your hearing mechanism. If you're a musician that plays very loud music, if you don't wear some hearing protection, you're going to damage your hearing over time. This is a very simplified diagram of the outer, middle, and inner ear. We're going to look at this quite a bit more tomorrow, this whole idea. But you have the outer ear. Air waves are funneled into your outer ear down the external acoustic meatus, and they are going to hit our tympanic membrane, our eardrum. There are 3 little bones or ossicles that are attached to your eardrum here, and they're all attached together, the malleus, incus, and stapes. These little ossicles act as a lever advantage, so we don't lose as much sound energy as we're going through the inner ear. And the tympanic membrane is larger than the stapes foot plate, so you get some mechanical advantage there. And let me be more precise in what we're talking about here. When you have sound waves, they're out here, pressure waves. If you don't have these mechanisms to reduce the loss of energy of these sound waves as they're traveling from the outer ear to the inner ear, we would only get less than 1% of the sound energy delivered to the inner ear. And we couldn't hear, we'd be deaf. Because of 3 mechanisms, we get about 80% of the energy that was out here to our inner ear. What are the 3 things? In the external auditory meatus, it acts as a resonant column, and that amplifies certain frequencies. Resonance, it gives more energy. If you have a bridge and it swings and there's more wind, you can get the resonant frequency and the bridge could come down. So you get the resonant frequency, save some energy. Number 2, the ossicles, the little bones, provide a lever mechanical advantage. We know the principle of a lever. If you have something heavy to lift, you try to lift it here that's hard, you put a crowbar and use it as a lever, it takes much less force to do the same amount of work. And 3, the eardrum has an effective surface area about 17 times greater than the stapes foot plate. Let's say a little bit more about that. The tympanic membrane or eardrum right here has a bigger surface area. It's being condensed down to the malleus, incus, and stapes. The stapes foot plate is this base plate right here. The surface area right here is much less of the stapes foot plate than it is in the tympanic membrane. So you compress that energy into a lower surface area. Those three mechanisms enable us to get about 80% instead of about 1% of the energy into our inner ear. Sorry, we're a couple minutes over. Busy people. So have a wonderful day. See you tomorrow.